Hi everybody. Today's lesson is going to be on graphing linear and quadratic inequalities, and primarily quadratic because I think you guys have done a little linear before. But this is definitely different than our direct variation, which is what we left off with in our last class. So I'm going to start a new note, and I'm going to title it Quadratic Inequalities. In fact, you know what? Let's start it with linear inequalities, and then we'll do quadratics in just a minute. So I just want to do a little review. And before I forget, I'm actually going to back out in my notes, and I'm going to retitle that note sheet, and you guys probably should do this. I'm going to retitle it Inequalities. Because we will eventually then take one quiz over all inequalities. So we're going to do some linear, some quadratic, some absolute value. We might do some rational functions. We're going to do all kinds. So let's start off with linear inequalities. And so an inequality means that it's not equal. So it's kind of equal. It's either like greater than equal, greater than or less than. So something like this would be a linear inequality. We want to know y is greater than negative 3/2 x minus 1. All right, so for this, to look at this graphically, we kind of treat this inequality sign as an equal sign and graph y equals 3/2 x minus 1, but then we're going to have to play with that a little bit. So if I were to graph y equals 3/2 x minus 1, I have a slope of negative 3/2 and a y-intercept of negative 1. So this is going back to those Algebra 1 days. So I'll put a couple tick marks, put 5 in each direction. And I have a y-intercept, I'll make that green, of negative 1. And I'm going to go down 3 and to the right 2, or up 3 and to the left 2. And if I connect those with a line, that would be if it were an equation. Okay, but of course it's not an equation. So I'm going to make it a dashed line because numbers that are on this line are numbers that make the left side equal to the right side. Well, we don't want them to be equal, we just want to be greater than. So things that are on this line, this is our border. So what I'm going to do is I'm going to erase that, and I'm going to connect those with a dashed line. So it would be dashed if our inequality looks like this, if it's greater than or less than. If it's greater than or equal to, I then would make that solid because I then would want to keep those as part of my solution. All right, so far so good. Now I have to shade either above that line or below that line. And so I think one easy way to do that is to plug in a certain value. So, you know, I see this does not go through the origin. So the easiest value to plug in is typically 0, 0, or you could plug in 1, 1, or anything. And I think I'm just choosing positive numbers. If I plug in 0, 0, and it makes this a true statement, that means that everything on top of the line will make it a true statement. And so therefore I would shade on top of the line. If 0, 0 makes this a false statement, that means that nothing up here is going to work, so I'm going to have to shade everything below the line. So I will plug in 0, 0, 0 for x and 0 for y. So I get 0 is greater than negative 3/2 times 0, of course, is 0, minus 1. And so that is a true statement, right? 0 is greater than negative 1. And since that's true, that means everything above that line is going to make this a true statement. And so I would shade all of that area above the line. Okay, so for a linear inequality, we want to treat it as an equal sign, and then look to shade either above or below the line. And then the line would either be dashed or solid. So another quick example of a linear inequality would be something like this. Let's say we had, and I'll make this a little harder, so negative 5x plus 3y is less than or equal to 18. All right, so we need to do a little algebra here to get this going. So I want to get y by itself, and so I'm going to move everything to the right side. I'll move the negative 5x over, so I have 3y is less than or equal to 5x plus 18. Of course, these are not like terms, so I can't combine those. And I'll divide everything by 3. So y is less than or equal to 5/3 x plus 6. So now it is my inequality. I'm going to graph this thing. So I'll treat it as an equation. So I'll make my graph, put 5 tick marks in every direction. I have a y-intercept of -6 and a slope of 5/3. So my y-intercept is, let's make that green, down here at -6. My slope is positive 5/3. So from that point, I'm going to go up 5 and over 3. There it is. Okay. And then from there, I could also go up 5 and over 3, just to make it a little more accurate. Now, in this case, I do want less than or equal to, meaning this is going to be a solid line because I have the equal sign here, okay? So I do want to keep the values that are on the line, on the border line. And now I need to figure out, am I going to shade above or below? So I will again plug in 0, 0 and see if that works. If it works, I'll shade above. If it doesn't work, I'll shade below. So I get 0 is less than or equal to 0 plus 6. All right, well, this is a true statement. Okay, so 0 is less than or equal to 6. That means that 0, 0 works, so I should shade everything on that side of the line. And again, if that was a false statement, I would shade everything on the other side of the line. All right, so the difference between linear and quadratic inequalities are, of course, the function. So let's then move on to quadratic inequalities. And so this would be an example of a quadratic inequality. So we had x squared plus 6x minus 16 is less than 0. All right, well, we could do this a couple of ways. Instead of looking at graphically, which I'm going to show you what's happening graphically at the end, I'm going to take a more algebraic approach, and I'm going to, again, think of that as kind of an equal sign so that I could come up with my boundary points. So if this were an equal sign, I could factor this quadratic into x plus 8 times x minus 2. And so that means that my boundary points are at -8 and +2. So I'm going to just use a number line here. And let's say -8 and +2 on a number line. And that splits the number line into 3 regions. It splits it into stuff less than -8, stuff in between -8 and 2, and stuff greater than 2. And since these are my 2 boundary points, I'm going to test each region to see if numbers in here, here, or here make this a true statement, which of course is the same as this statement. So I'm going to see if they make it true or false. All right, so let's plug in a number. Let's say we plug in -100, and I chose -100 as an extreme value because when I plug that in, I know that negative 100 squared is going to be a large positive number. Okay, so that's going to be really big positive. And this is going to be negative, but not nearly as big. And this is going to be negative and not nearly as big. And so the question is, if I have this real big positive number, minus this, okay, it's all going to be positive. And is a big positive number less than 0? Well, no, it's not. Okay, so that part does not work. Then I would choose a number in between negative 8 and 2. 0 is always a nice number. And so if I plug 0 into the original equation, that's 0, and that's 0, right? Because 0 squared and 6 times 0. So I'm left with negative 16 is less than 0. That is true, which means this part does work. So instead of, I guess, that x, maybe I'll say yes and no. So this does not work. This does work. And then I'm going to choose a number larger than 2. So again, an extreme value like a million. A million squared is a big positive number. And 6 times a million is a big positive number. So the whole thing is going to be positive, which is not less than 0. And therefore that does not work. And so my solution then is going to be stuff between here and here, but excluding the boundary points. Why are they excluded? Because I only want to make stuff that makes it less than, not less than or equal to. So in interval notation, we are from negative 8 to positive 2. Now graphically, what's happening is you have a parabola opening upward. It has x-intercepts at negative 8 and positive 2. It looks something like this. And this is saying, when is it less than 0? Well, it's less than 0 here. And so that's from negative 8 to positive 2. So just to give you a little visual of what's happening graphically. But algebraically is how I'm going to go about solving most of these. All right, let me give you another example. So our next example, let's say we have x squared minus 13x plus 40 is greater than or equal to 0. So like before, I'm going to try and factor that. If it doesn't factor, I could use the quadratic formula, but it looks like this is going to factor into x minus 8 times x minus 5. And I'm writing this as an equation just because I'm trying to find my boundary points. So now my boundary points are 5 and 8. And I need to test the 3 regions, here, here, and here. So I'll pick a number to the left of 5. And again, you could do an extreme negative value, but I think 0 is always an easy number to plug in there. So I plug in 0, I get 0 and 0, so I get 40 is greater than or equal to 0. That is true, and therefore this part works. Something between 5 and 8, so something like 6. So if I plug in 6, let's see, 6 squared, it's going to be 36. And I have to do something specific in here, right? Because it's a finite area. So I'm going to do 6 squared is 36. And then 13 times 6 would be 72. Whoop, I'm sorry, 78. Plus 40. Okay, so that is going to be a negative number. And since that is a negative number, that is not greater than 0. So that is a no. And then I'm going to plug in something in this region. So an extreme value like a million. So if I plug in a million squared is a big positive number, okay, which is going to greatly outweigh this number. And therefore, that is going to be positive, which is greater than or equal to 0. And so my solutions are going to be here and here. Of course, I need to keep the boundary points as well because it is greater than or equal to. So my solutions would be from negative infinity to 5, inclusive, union, and then from 8 to infinity. Okay, and again, graphically what's happening here is you have this parabola with your intercepts, and the question is saying, well, what's happening? When is it greater than 0? Well, it's greater than 0 here and here, and so that is corresponding to those regions. All right, so I'll do a couple more, but the only difference or the only thing that would change would be the type of function that we're looking at. So if I had something like 2x squared minus 27x is less than 7x minus 140. Okay, it's just uglier. All I got to do is get everything on one side. So I'll move everything to the left. So I have 2x squared minus 34x plus 140 is less than 0. Looks like I could divide everything by 2. Okay, and I said less than, I really am thinking of that as an equal sign. So let's say x squared minus 17x plus 70 is equal to 0. And with any luck, that one will factor, which it does. And I know I'm going kind of quickly here, but just to show you, the only difference is that we're looking at, changing the difficulty of the algebra there. But once I get down to here, of course, they're all really the same. I have my boundary points at 7 and 10. I will test something to the left of 7, like 0. And if I plug 0 in, and I'll plug it in here, I get 140 is less than 0. That is not true. Then I'll plug in something between 7 and 10, like 8. Okay, well, if I plug in 8, I'm going to do 2 times 8 squared minus 34 times 8 plus 140. So that might be, a calculator question. So luckily I got one here. All right, so I have, come on, there we go, calculator. We have 2 times 8 squared minus 34 times 8 plus 140, and I get negative 4, and negative 4 is less than 0, therefore that part worked. And then I'll plug in something to the right of 10, like a million. And so if I plug in a million, this will be a huge positive number, which will greatly outweigh those things. And that is not going to be less than 0. And so I have my solution area is between 7 and 10. It is exclusive of the boundary areas because I'm not less than or equal to, I'm just less than. So my answer is going to be from 7 to 10. All right, last but not least, my last example. If I had negative 6x squared plus 9x is less than or equal to negative 2x minus 2. So I'm going to solve this just the same way. The only difference in this one, if I get everything on one side, that gives me negative 6x squared, and that is plus 11x. And plus 2 is less than or equal to 0. And the only difference is this one is a little bit more difficult to factor because we have a leading coefficient other than 1. So one thing I do notice is that this is a negative out front. And since I'm thinking of this as an equal sign, I can divide everything or multiply everything by negative 1, giving me 6x squared minus 11x minus 2 is equal to 0. And then I could look to factor that, and I think with any luck it is going to factor. Of course, I could use the quadratic formula. Let's see, we're going to have 2 and 1, right? If I had negative 12 and positive 1, which means my boundary points are going to be 2 and negative 1/6. So I again would draw my number line. I have negative 1/6 and positive 2. I would test my 3 boundary areas, and then I would write my solution accordingly. So I'm going to leave that up for you guys to finish, because I think that I've kind of gone through, and this has gone a little longer than I expected, but we went through our linear inequalities and our quadratic inequalities, and so now it's going to be time for you to work on your